So in the series of learning Python programming language, we are discussing operators in Python. Till now we have discussed arithmetic operator, assignment operator, comparison operator and logical operators. The next is bitwise operator. So these operators we will be discussing in this video. Okay, which are bitwise operators, like what are bitwise operators, how to use them. With the help of example program, we'll be seeing the working of bitwise operators, and I'll show you on my laptop also, right? The notes of this lecture you will get in the description box of this video. I'll put the link. You can click on that link and you will get the notes for this class. Okay, now see, as the name suggests, bitwise operators. So these operators works on bits. You can say binary numbers. Like same in C and C++ also we have discussed bitwise operators. So they work on bits actually. They used to operate on binary numbers, on bits. Now how they are going to operate? First of all, let me tell you what are bitwise operators. We have bitwise AND, bitwise OR, XOR, then we have complement, or you can say NOT, then we have left shift, and then we have right shift. So these are bitwise operators. So first of all, we will be discussing the working of bitwise AND operator. See, let's see. We have A is equal to 5 and B is equal to 4. Rather than in 2 lines, you can do assignment in 1 line only. Okay. Now, if I want to print, like print A and B, I want to do A and B. This AND is for bitwise AND. So this AND is going to perform on the bits, not on these numbers. So first of all, convert these numbers into binary numbers. So now A becomes what? 5 is 101 and B is what? 4, 100. Or generally we represent numbers, means these decimal numbers in either 4 bits or 8 bits. So let's represent in 4 bits. Okay. Now I hope you know 5 is 101, like, or you can say you can calculate this 1, 2, 4, 8, something like this. So 4 plus 1 is 5 and 4, this is 4. At the place of 4 only we have 1 only, right? So now do bitwise AND. Bitwise AND means same. If both are 1, then only it will give 1, otherwise 0. So 1, 0, 0, 0, 0, 0, 1, 1, both are 1, it will give 1, 0, 0, 0. So now convert this number into decimal number. This would be 4. So the answer would be 4. Okay. So bitwise AND same will give, if both are 1, then only it will give 1, otherwise 0. Okay. Now let's see. We have bitwise OR. The next is bitwise OR. Now A is this, B is this. So bitwise OR. Now what is the result of this thing? Bitwise OR means it will give 0 if both are 0. If any one is 1, any one of the bit is 1, it will give 1. So 1, 0, 1, 0, 0, 0, 1, 1, 1 and 0, 0, 0. So now convert this into decimal number, it would be 5. So the result of this would be 5. Logical and these are bitwise AND and bitwise OR. Now bitwise XOR. What would be the output? See, bitwise XOR. Now bitwise XOR means what? If both the bits are same, then it will give 0. It will give 1 only if bits are different. Let's see. 2 bits, 1 XOR 0, 1 XOR 0, both bits are different, so it will give 1. 0, 0, both bits are same, 0. 1, 1, both bits are same, so it will give 0. 0, 0, both bits are same, so it will give 0. So the decimal of this is what? 1, so it will give 1. So I hope you got working of bitwise AND, OR and XOR. Now this is little bit tricky. So let's understand this complement operator now. If you print, if you do negation of A and if you print this thing, it will give you, A is 5, so negation of 5, it will give you minus 6. How you are getting minus 6? This is a little bit tricky. Now let's see. This NOT will reverse the bits. If bit is 1, it will be 0. If bit is 0, it will be 1. So now let's see. Negation of 5. 5 in binary we have 0, 1, 0, 1. In 4 bits I am representing the number. Okay. 1, 0. This is 5. Now negation of 5 would be reverse the bit. 0, 1, 0, 1. So this would be negation of 5. Now what is this 1, 0, 1, 0? Maybe if you apply that logic like 1, 1, 2, 4, 8, you will say it is 10. So it should give 10, not minus 6. But how we are getting minus 6? See, it is not 10. We are getting minus 6. So see, we cannot store negative numbers actually in memory. Okay, we have to convert this into positive number. So yeah, there is a method to store negative numbers in memory. Now what is that method? 2's complement. We have to find out 2's complement of the number, then we can store that negative number into computer memory. Okay, so this is minus 6. If you are going to store this minus 6 into computer memory, first of all convert it into positive number, find out the 2's complement. Now 2's complement is what? 2's complement is 1's complement plus 1. I guess you are aware about these things. If you have I think read Boolean algebra, in that we have these kind of things. Or in basics of programming also, computer programming also, in the first chapter we have these things. Or in digital electronics, one subject is there, in that also we have these things. So 2's complement is 1's complement plus 1. This is 1's complement, like 1 apostrophe s. This is apostrophe s. Now how to calculate 1's complement? 1's complement we can get simply by reversing the digits. Means if there is 1, reversing the bits, sorry, not digits, bits. If 1, then 0, if 0, then 1. Okay. Now we have to find out 2's complement of 6. So 6 in binary, how we represent 6 in binary? This is what? 1, 1, 0. 4 bits I am taking, so this is 6. Like 1, 2, 4, 8. 4 plus 2 is 6. Okay. Now 1's complement of 6. Just reverse the bits. 1, 0, 0, 1. Now 2's complement, add 1. Add 1. So you know, I hope you know binary addition. Binary addition, 1 plus 1 is 0 plus carry 1. So 1 plus 1 is 0, carry 1. So 1 plus 0 is 1, 0, then 1. So 2's complement is this one. See, binary addition of is the digits are 0 plus 0 would be 0, 0 plus 1, 1, 1 plus 0, 1, 1 plus 1, it would be 0 with carry 1, okay. So now 2's complement of this is 1, 0, 1, 0. This is how we store minus 6, and this is exactly negation of 5, 1, 0, 1, 0. That is why we got negation of 5 is minus 6 always. So simple method is what? Negation of any number, like negation of 10. If you will do, simply you will get that number plus 1 with minus sign. So it will you will get minus 11. Okay. I hope you got how this thing works. Okay. Why we are getting the result of this not or this complement, we say it complement also, this complement operator, something like this. I hope you got this thing now. Okay. Now next is left shift. See, this is also very interesting. Now if I left shift this A, left shift 2. Okay, so it is going to left shift the first operand with respect to second operand. So first operand is A is 5. So we are going to left shift 5 by 2 bits. This is what? Bits. Here you can write down 1, 3, 4, 5. Any number of bits you can write down. It's not like that you have to write down 2 only. Okay. Now A is 5. So 5 in binary we have 101. We write it as 10101. This is 5. Now left shift by 2 bits means this side we are going to shift by 2 bits. Okay. So here we are not going to discard the, maybe you will say just left shift by 2 bits, discard these 2 bits. So 0, 1 and add 2 zeros. At the right hand side, the remaining places we will add, we will fill those places with 0. So this would be the case. No. We are not going to discard these bits. Remember this thing. Okay. So left shift would be what? We are going to simply add left shift 2 bits like 0, 1, 0, 1. So here we have places of 2 bits remaining. So simply add 0, 0. See, generally if I write 5, so it is 5.0. 2 means 2.0 with floating point number. After floating point also we have something. 0 is 0, 0, 0, something like this. Okay. Now, so if you left shift this you can say 0, 0, 0 this time. If you are going to left shift this, these 2 zeros would be shifted to this one. We are not going to discard these 2 bits. We will keep these 2 bits. Okay. If zeros are there, you can discard zeros. Like if in 8 bits I represent 5, 0, 0, 0, 0, 0, 1, 0, 1. In 8 bits, this would be 5. In this case, we simply can say, because these are zeros you can discard. Simply we can say left shift this side, so discard these 2 0. So this 0 would be at this place. Now this would be at this place. Here we have 0, here we have 1, here we have 0, 1. Now remaining 2 places we will fill these places with 2 zeros. That can be a case. But here in 4 bits, 2 bits are 0 and 1. We cannot discard this 1, otherwise we will get some unexpected result. Okay. So in left shift, we always gain bits. We are not going to lose anything. Okay. I hope you got my logic here. So now see, so this you will get after left shift by 2. So now what is this decimal number? 1, 2, 4, 8, 16, 32, something like this. So 16 plus 4, 20. So this would be 20. Simply the formula is what? If you left shift, like x is a number, if you are going to left shift this number with n bits, so what output you will get? This x into 2 raised to power n. See here, x is 5, 5 into 2 raised to power 2. It would be 4. That is 5 into 4, that is 20. Okay, this is left shift. Now what about right shift? See, if we right shift this a by 2, then what result you will get? Now a is what? 0, 1, 0, 1. Okay. Now right shift by 2, we are going to right shift by 2 bits. In this case, we will lose bits. We are going to discard. So right shift by 2 bits. So these 2 bits would be discarded. So here we have this one would be at this place, this 0 would be at this place. Now these 2 bits, these 2 places would be filled with 0. So this would become now 1. So the answer would be 1. In this case, in right shift, we will discard the bits, means we are going to lose the bits. But in left shift, we gain bits. We don't lose. I hope you got this thing. Okay. Because this 2 bits, maybe you can say after decimal we have 0, 0. So these 2 bits would be after decimal. So we are going to discard these 2 bits. So if right shift by 3, then 3 bits we are going to discard. So this 0 would be at this place, the remaining 3 bits would be full with this 0, so the answer would be 0. Okay. Now, here we have answer 1. So simple formula is, if x would be right shift by n bits, then the answer would be x divided by 2 raised to power n. So here x is 5, 5 divided by 2 raised to power 2, that is 1. 5 divided by 4, that is 1. Okay. So this is right shift. So I guess you got the working of these operators. Let me just show you practically. We will see these things practically, and then I'll give you one exercise also. Okay. Okay. Now we will take this. Here we will take 2 variables, a5 and b4. So we are going to just print a bitwise and b. Okay. Let's see what output you will get here. You will get 4. If you print a bitwise or b, in that case what you will get? You are getting 5. Here you are getting 5. Now if I print, let's try with XOR. A XOR B, the last one, will get 1, right? And we simply print not A, or you can say complement A. This is bitwise not, or you can say complement. So this will give you -6. Not B would be your assignment. If you print not B, then what it will print, you have to try. If I print like A left shift by 2 bits, so then you will get what? It would be 20. See, it would be 20. And if I print like A right shift by 2, what you will get? It would be 1. See, the last, it would be 1. So if you are aware about, if you got the working of these operators, you can try out with different different values and all. It's not like that you can only try with 5 and 4. It's not like that you have to left shift or right shift by 2 bits. You can do with 1 bit or 3 bit, 5 bit, 4 bit, up to you. So now I'll give you one assignment. So this is for your assignment. You have to tell what would be the result of these things, okay? Rather than simply just, going to your ID or laptop and just print these things. No. First of all, try out at your own without your laptop. Then run this thing on your laptop, like print, and you can tell your answer. So this 26 and 23, 17 or 24, 17 XOR 24, negation, or you can say complement 45, not 45, 68 left shift by 2 bits, 56 right shift by 3 bits. So I guess you can do this. You are aware about these bitwise operators now. So now 2 special operators are remaining, identity and membership operator. Those things we will discuss in next video. So now it's in the next video. Till then, bye bye. Take care.